The last idea we want to look at in this topic of combinatorics is this idea of the pigeonhole principle. And it's actually a fairly straightforward idea when you think about it. If you've got n plus 1 or more objects, and you're going to place all these objects into n holes, then at least one of them must have more than one object. Because how could you put n plus 1 into n holes and only have one in each hole? Couldn't do it. Here's I guess it's a proof. So alright, let's let k be the maximum number of objects you can put in n holes without having more than one in a hole. Let's prove that that's going to be less than n plus 1. I'm going to do it by contradiction. I'm going to assume that you actually can put more than n objects into n holes. The maximum number of objects must be n. In other words, each hole has one object. That would be the maximum number. So k has to be less than or equal to n. But hang on, I've assumed k is greater than or equal to n plus 1. Straight away I get a contradiction. Thus, it can't be true that k is greater than or equal to n plus 1. So k has to be less than n plus 1. I don't know how great a proof that is, but that's the sort of logic behind it. Alright, to generalise that, if k or more objects are placed into n holes, then at least one hole must contain k over n, and there's this notation. That notation, the ceiling function, or more objects. And so the ceiling function technically is this. Basically it just means you always round up. Whatever your answer is, you always round up. Okay, let's look at some questions there. We've got a set of integers there going from 3 to 12. And we're going to get some of these integers. What's the least number of integers I could pick from that set to ensure that I get a pair of numbers that adds up to 15? Well, if I look through that set, there actually are 5 possible pairs that would end up to 15. There they are. And folks now say, well, hang on, they're my holes. That's where I'm going to put the object. So imagine you've got those holes, and I'm going to pick a number out of the set and put it in the appropriate spot. So I pull out 7, I'll put it in this last pigeonhole over here. I'll pull out 10, I'll put it in the third one, and so on and so on. I must have 6 numbers in order to ensure I get 2. Because you see, it is quite possible that when I pick these numbers out, I went, 3, 11, 6, 10, 7. I've now got 1 in every hole. But now, when I pick the next one, I must end up with a pair of numbers that end up in 15, because it has to go in one of those, and they now all have 1 in it already. If I use the ceiling function idea, then I can say, well, what I'm saying is k over 5. So objects into the holes. That's how you can think of that fraction. Objects into holes. Objects into holes. So k over 5, and we want that answer to be 2. There's the inequality. That means k over 5 is in between 1 and 2, but not including 1, which means k is in between 5 and 10, not including 5. We want the smallest number, the least number. Well, the least integer that satisfies that inequality would be 6. So I could use that little formula if I'd wanted to on that question. We're going to prove that in a group of n people, there will always be 2 people with the same number of friends in that group. It's not possible for a person, one of those people, to have no friends and another person to have n-1 friends. That would be impossible. So therefore, I'm going to assume that the number of possibilities of this, you could have 1 friend, 2 friends, 3 friends, going up to n-1 friends. I'm going to assume no one there has no friends. So there are n-1 different number of friends a person could have. They're the holes. So by the pigeonhole principle, because remember we've got n people, and we're putting them into n-1 holes, so there must be at least 2 people with the same number of friends. 16 positive integers are going to be written on the board. Just randomly picked. I mean, you're just going to randomly select them. There are 5 possible remainders. It could go in exactly. You'll have a remainder of 1, 2, 3, or 4. So we're going to place these 16 numbers, 16 objects, into the 5 holes. The holes now are like the remainders. I'll use the ceiling function idea there. Objects into holes, 16 on 5. Find the ceiling function of that. Ceiling function of 3.2, always round up. So that's 4. So I know there are at least 4 numbers that would end up with the same remainder if we did that. Alright, we're going to generate random 3-letter words. And as far as we're concerned, any combination of 3 letters is a word. So how many words does this computer need to generate to ensure that the same word comes out 8 times? Same word comes out 8 times. How many possible words could we have? There's 26 possibilities for each letter. So by our basic counting principle, that tells me I've got 17,576 possible words this computer could spit out. That's our holes. I won't write them all up on the board, but the word's going to get spit out and we'll put it in the appropriate slot. We want to know how many objects. So K into 17,576 holes should give me the answer 8. That's what I'm looking for. Going back to that inequality then, it must be in between 7 and 8, not including the 7. Multiply out the smallest integer that would be bigger than 123,032. So we need 123,033 words for this computer to spit out, and that will guarantee that we had the same word generated 8 times. Let's have a look at some HSC questions then. The Sports Association manages 13 teams. It decides to check the age of all players. Any team that's got 3 players above the age limit is going to be penalised. They've done their survey. They found 41 players above the age limit. And the question simply was, is any team going to get penalised? I'll use the ceiling function idea. 41 players into 13 teams. We found these 41 illegal players, and the slots are the teams that they're going into. So 13. That has to equal, well, what does it equal? 41 divided by 13, rounded up, is 4. So yes, at least one team will have 4 or more players above the age limit, because that tells me that the ceiling function there is 4. A team will be penalised. Last year's question, Students from 4 different schools come together to form a choir. What's the minimum size of the choir to know that there must be at least 20 students in the choir? Minimum size of the choir to know that there must be at least 20 students from the one choir. So again, we want to know K divided by 4. How many objects? What's the size of the choir? How many students are we putting into the pigeonholes, which would be the schools? We want that answer to be 20. Good, put it into the inequality. Okay, biggest number, 77. What's the biggest number? Smallest number, 77. So minimum size of the choir would be 77 students. All right, let's move on to the exercise.